There are other cases where that whiskeys for drinking, waters for fighting has come into play, and that is a 1980 or 1892 court case, Power versus People. And what happened was Mr. Power owned some land, and Mr. Bear actually had some water rights. So there was an irrigation ditch that ran from a stream through the Power's land onto Mr. Bear's land. And the Powers, there was a brother and sister, they wanted some of the water rights from that ditch. Well, this happened in the arid West, where water rights are first in time, first in right. It didn't matter that the ditch was, or the initial water supply was running through the Powers property, or that the irrigation ditch ran through there. Bear had the water rights. So there was obviously a fight. Mr. Power killed Mr. Bear. He was tried for murder and found guilty. He appealed his conviction, saying that, you know, he had to have the water, he needed the water, he shouldn't have been found guilty. And his conviction was upheld, and the court held that human blood is more precious than water, even in that thirsty land. So it's just another example of that whiskeys for drinking and waters for fighting, and it makes us think what's going to happen in the future with our water resources. And, you know, we've seen it in Oklahoma. We've seen it happen between Oklahoma and Arkansas, where there have been court cases over either water quantity or water quality. And are we going to see those cases increase? I noticed on the list of who all was in the workshop this week that there's a lot of folks from the Water Resources Board. So some of this might be a little bit more elementary for you all, but some of it maybe not. So how do we measure water? We measure water in a couple of different ways. We measure it as acre feet. That's a lot of times how you'll hear a water right is so many acre feet, and an acre foot is 1 foot of water covering an acre of land, about 325,851 gallons. When we're talking about stream flow, stormwater flow, we're talking about CFS. You'll hear that abbreviation a lot, and that's cubic feet per second. So 1 CFS equals about almost a little over 645,000 gallons per day, or 1.98 acre feet per day. A lot of times when they talk about flooding, they'll talk about how many CFS, or when they're releasing water from a dam, it's how many CFS they're releasing. And then if you're a municipal water supplier, you might talk about it in million gallons per day, or MGDs. And that equals 1.5 cubic feet per second, or about 3 acre feet per day. So municipal water suppliers, they might ask for acre feet, but then when they talk about their treatment plant, they might talk about it in their treating or distributing millions of gallons of water a day. So they'll talk about it in MGDs. This is just an example from the Oklahoma Comprehensive Water Plan on estimated annual average stream flow, what we expect to see in 2060. So this was developed in, maybe 2010, 2009, kind of during the heart of the water planning process. And so you can kind of see that they're estimating, especially in eastern Oklahoma, anywhere from 1 million to 2.5 million acre feet per year in stream flow. Obviously, in the western part of the state, that's a little bit lower because A, it's more dry there, there's less surface water there. But we still have some areas where we have some decent flows. And then they also estimated total storage in acre feet in our aquifers. And this would be our alluvial aquifers. So we have, you know, the Canadian, the North Canadian, the Cimarron, the Salt Fork, and they've estimated total storage in those alluvial aquifers, which is that aquifer that kind of borders the stream. And then in our major bedrock aquifers, we're looking at the Ogallala and having estimated storage of, looks like over 90 million gallon feet of water. So seems like a lot. We'll talk a little bit more about that later. They've got the Ruby Doo on here, the Mimosa Ada, Garber Wellington. So you can kind of see how much water we think we have. And then let's look at those water uses. So in 2007, they went and looked at what the statewide water demands were. The biggest water user was crop irrigation. Next was municipal and industrial. If we look at oil and gas, it's just about 2% of water use. Livestock, 5%, thermal electric, 14%, self-supplied industrial, and self-supplied residential. Jump that up to 2060 to look at our projected demands. Crop irrigation still probably the largest, but municipality is getting right in there. Oil and gas jumps up to 5%. Livestock comes down a little bit. Thermal electric goes up, and then self-supplied industrial and residential stay, similar. So our total projected water demand in 2060 is about 2.5 million acre feet per year. So what are those water uses? With non-consumptive uses, the things that we don't necessarily always think about as being a water use, right? We have recreation, boating, fishing, swimming, that kind of thing. Tourism. I'm at Grand Lake right now, and I had breakfast with a friend, and she was telling me that since about March, where she works part-time is a marina, and they have some cabin rentals as well. She said it's been like high season the whole time because people are coming to the lake to quarantine, to isolate or whatever. Better to be up here maybe than wherever they normally live. So people are drawn to water anyway. So tourism is a huge use of water that we don't often think about, and it's very hard to figure out how to value it. Environmental flows. What about leaving some water in the stream for those organisms? That is a non-consumptive use. We're just kind of leaving it there, but it serves a purpose. Navigation. We have the largest inland navigation channel, I think, in the world, at least in the US. That takes water, but we're not pulling that water out and using it. We just need to leave it in place. And then hydroelectric power as well. So technically, yes, we've got water in a lake. When we release it, it's going downstream, but we're not pulling it out of the system, right? It stays within that same system. This is just sort of a snapshot of the water supplies that we have aquifer-wise, both the alluvial and bedrock aquifers. So, it could seem like we have a lot of groundwater out there. This is our surface water, streams, lakes, ponds, that sheet flow. And, it's an interesting map because you can see mostly in eastern Oklahoma, you have a whole lot more green. That's why they call it green country, right? Southeastern Oklahoma, a little bit of south central Oklahoma. And then as we move further west, we start seeing where that dry line really starts kicking in. However, one of the things that might be shifting is where that dry line is. There's been talk that we're already seeing it creep a little bit more to the east. So maybe our dry line is shifting, and some of this lighter green in here in another 5 or 10 years is going to be more of that brown, where we have less of that surface water. This is just, what is changing. And, I think we're still figuring it out. Yeah, we know that temperatures are increasing. We're seeing that. What about our storms? It seems like we're getting more rainfall, but in less storms. So we're maybe getting the same amount of rainfall throughout the year, but it's happening in fewer storms. So maybe we're getting increased flooding and things like that. I talked about temperature increase. This is just an example from the mesonet. This goes up into the 2010s. And you can kind of see historically we've had some cooler weather. That's what the blue is at the bottom, and some hotter weather. We've had some really hot weather. Let's go into the 1950s, right? And then into the 2011. We had some 12, we had some really hot temperatures. But what you're noticing, or what I noticed from mid 90s up until the 2000s, is we're getting a lot more on average higher temperature, right? Not that we don't have some years where it's cooler, but on average, it's been higher. We look in this period from the 60s up to the mid 90s, we had on average a lot more cooler temperatures. Not that we didn't have some drought in the 80s, a little bit in the 70s, we had some higher temperatures, but overall what we saw were cooler temperatures. And then when we throw in rainfall on top of that, and hopefully you can see this, you can kind of see a little bit, and it's not exact, but you can kind of see where we've had that cooler temperature on average. It's also been wetter. Not that we also haven't had cooler temperatures in dry times, but if you look starting in the mid 90s and carrying through, when we've had those hotter temperatures, we've also had increased rainfall, which we would expect when we have hotter temperatures. Maybe we'd have more drought, because historically that's kind of what we have seen. So what would be impacts that we might have to water quality? One would be from non-point source pollution, right? That's the largest uncontrolled source of water pollution in the US. And it includes those diffuse surfaces like urban and irrigation runoff, surface mining, and construction sites. Pollutants are going to be sediment, bacteria, oil and grease, nutrients, trash, animal waste, and salts. So everything that falls on the land and then it rains, it's going to carry all of that water into our streams and rivers, right? Because our stormwater system is not connected to a wastewater treatment plant. It dumps directly into a stream or river. So what does all that mean? And especially as we have larger influxes of rain, maybe in the spring, we have those large, a lot of rain in the spring, and then we get that period in July or August, sometimes even June, where we get super hot temperatures and we get less rainfall. Maybe we go into a little bit of a flash drought. What impacts are those going to have? So other changes besides the timing of the rain, the amount of rainfall that can affect water quality, are land use changes, changes in how we manage the land, and then how we educate landowners in how those changes that they're making can make that impact. And then some of the impacts from this climate variability, where we maybe have this heavy rains in the spring, hot, dry summer, is we'll end up with lower dissolved oxygen. We've got an influx of nutrients in the spring coming into our water systems. So we get that, have a lot of algae maybe in the system in the early spring, early summer. We also are maybe getting more increased pathogens and nutrients, E. coli, Enterococcus, maybe some more bacteria than we've had normally. We're seeing increases in invasive species. Either they're moving up because it's warmer here now, they can stay here longer, or they've been brought in and now they're in more of a climate that they live in. Increased algal blooms. This picture down here is Grand Lake from the summer of 2017, where they had another blue-green algae bloom. You think about last summer, with several even small neighborhood ponds that had toxic blue-green algae blooms. There was one in Norman, there was one in Edmond at the dog park, and that's something that maybe they hadn't dealt with before, and now we're seeing maybe more harmful algal blooms as well. And then we might have a loss or a change in those aquatic species as habitat changes, because maybe we either we're getting more vegetation because we're getting more water, it's hotter, we're going maybe a little bit more of a tropical climate. We might see changes in aquatic species that maybe didn't thrive before that now can thrive, and there's going to be a loss in some species that can't thrive, or we're getting new species moving north, and the species that we're used to having here are also moving north because now they can live further north. So we're going to see some change in those aquatic species as well as the terrestrial species in terrestrial and aquatic vegetation. So impacts to water quantity. I mean, this is a really good example, right? We've got, this is Canton Lake. You know, we can have lakes go completely dry, and then within a very short period of time, we can be reversed into flooding. So how do we plan for that? How do we manage our water resources to plan for times like this? And you think, well, you know, we look at past history and think, well, we've had, you know, this much rain on average through this time period, so this is what we can expect. But I think we're going to have to shift, and we're not going to be able to look at we're going to have to look more at the near past versus the long-term past to see how things are changing, so we can help plan for the future. So we're very used to looking at the long-term averages and looking backwards, but as those begin to shift, maybe we're going to have to start looking more near-term historically to figure out how we're going to manage for these, to ensure that we have the water supply that we need. What about that supply versus demand? When you think about it, you think about Canton Lake, that's one of Oklahoma City's water supply. Now they're working to bring water up from Southeast Oklahoma, but how sustainable is that long-term, right? And what about the people in that area? Tulsa does the same thing. They get their water supply mostly out of Northeast Oklahoma. So what impact is that going to have on the communities in Northeast if that water needs to go to Tulsa for their demands? If we have increased supply, awesome, right? But the reality is maybe that's not what we're going to have. And so we've got to figure out how to balance those. Water quality can also impact water quantity, right? Because if it's not treatable water, then it's not necessarily usable water or readily available for us to use. The other thing is we get fluxes and we have more nutrients in the water system or more water quality issues, then the water becomes more expensive to treat. So then our costs go up, and then we have to have a rate hike, and nobody likes that, right? So, you know, the water quality can have a couple of different impacts that we maybe hadn't thought about in the past, or it's been a minor inconvenience to maybe deal with some algal blooms when we treat our water. Maybe now that's going to be more the norm. And then those consumptive versus non-consumptive uses. Oklahoma's blessed with a lot of water in the eastern part of the state, right? And that's where a lot of tourism happens, is in the eastern half of the state. What about that? And who takes precedent? Because they're both economically feasible. I've been at GRDA teaching a workshop for a couple of days, and we got to talking about the big blue-green algae bloom that they had back in 2011 that shut the lake down over the 4th of July holiday. So one of the big issues was the tax dollars in the 4-county area that surround Grand Lake. It was just going to devastate the economy, right? Because now you don't have that tax coming in. What actually happened in reality, even though people couldn't get on the lake, they were still up here, and the taxes actually went up because people were now in bars and restaurants. Their fuel tax did go down, but the sales tax went up because people were eating out more and they were still here, but the economics of it switched. Also, those non-consumptive uses for hydropower, if our hydropower lakes are also a drinking water supply like Grand Lake and some of our other lakes like Canton, or Canton's not necessarily a hydropower lake, but Fort Gibson, Hudson, Grand Lake, you know, they have contracts with the Southwest Power Pool. They've got to supply a certain amount of electricity to them. They get that through the hydropower. If their water levels go low, what happens to that lake as they're still trying to produce hydropower? So they're having to look at divesting and having other maybe energy sources besides just the hydroelectric power. So GRDA, for example, has some wind power. They have, they just issued an RFP for some solar power to help augment their supply. they have a natural gas plant and they have a coal plant. Although coal-fired plant, they provides like a minuscule amount of their electric. It's either wind, hydroelectric, or the gas. And then they have the Salina pumped storage facility, which is what this picture up here is, which is kind of like a battery, right? They pump water up into a reservoir, and then at night, usually when the electric prices are cheaper, and then when they need electricity, they can gravity flow it back out and turn some turbines. So it's technically like a battery storage with water. But if they don't have the water there, then they can't necessarily produce that electricity. And then what about those in-stream flows? You know, we just have, we have some endangered mussels in the state. We have some other endangered species that require a certain flow of water. We don't necessarily really have an environmental flow policy in the state of Oklahoma, although, you know, there is a domestic use set aside that can sort of be considered by some as providing some environmental flow, because the assumption is that not every domestic use along the stream is going to pull their water out. But when you're dealing with dams, maybe they don't have any requirement to release for environmental flows. You know, how do we manage that? Because without that flow, without some water in the streams, right, we're going to impact our aquatic life. And then we're going to have increased evapotranspiration. We've seen increased flooding already. And then what about our infrastructure needs and maintenance? I'm going to hurry up because we're about done. Land use practices, agriculture, urban, can make a bit of soil health to make some changes. We're also seeing some urban soil health push to change how we manage our lands, putting in low impact development, green infrastructure. How are we going to manage those supplies? What are our water needs really going to be? And how do we calculate that? And what about water quality? And those are just some of the things that you can think about. And with that, I'm happy to answer any questions with the few minutes that we have left.